All right, so recording is on. Let's share that screen. All right, so here was the Desmos activity. All right, and the first part had you looking at problem solving strategies. Okay. And so looking at this one, I did work out this example for you, like, okay, we know how to do this because we can sort of multiply it out, and then we can use the power rule to solve the derivative of 3x minus 5 squared. Okay. Were there any questions about this slide? I'm going to take that as a no because it's an example. So duh, Judy. All right, what might be some ideas that we write down for example 2 here? All right, if you had an idea, go ahead and type that into the chat. How would we approach this question? We could FOIL this one for sure. Yes, this should have been the first part of this. Should have been the first part of it. No?
I think our first part was like the inside and outside functions.
Did you not have this first part? Okay, I don't know what's going on. Okay, you know, sometimes we just chalk off the whole week as things are not going smoothly the way they are. Okay, maybe then let's actually do this because this is important for today. Okay, so now that you're seeing this for the very first time, let me give you some appropriate think time on how you would solve this. Okay, so Graham had a great idea. I know, what a week, right? Graham had a great idea. He said that maybe we could FOIL this out. So we might write like square root of x plus 2 times the square root of x plus 2 times the square root of x plus 2, multiply it all out. And then I think we should be able to use power rule for that. Okay. Does that make sense to folks for as far as the strategy for number 2? Okay. Sorry for sounding like a jerk. I was like, why is everyone being so quiet? Okay, here we go. All right, so for the next example, we're also going to sort of brainstorm together about what rules and methods we could use to solve this, okay? So let's take a look at this one. Example number 3. Let me give you a few moments to think about that. But how might you approach y equals sine x and then squaring that whole thing? How would you try and find that derivative? Yeah, Moon, that's a great idea. We could certainly, let me try annotating. Let's see how this goes. Because, you know, the tech is going so well for us this week. Okay. So if we had y equals, can you see that, by the way? Yes, okay. So sine x, if I square it, is sine x times sine x, right? And so that's a structure that I want us to make sure we can see, that when we have sine x and we square it, it becomes sine x times sine x. And then we could certainly use the product rule, okay? What is another way of writing sine x squared? Because I don't think we normally see it like that in a textbook or in a computer program. How do we normally write that? Oh, okay, we could do that. I was thinking, yes, I was thinking more without a trig sub. We usually see this as sine, and then there's like a squared here, and then the x, okay? And so that's actually a structure I wanted to make sure was really visible for us, where if we're looking at sine x squared, it is the same thing as saying y equals sine squared x, okay? Now, depending on who you had for trig, that may or may not have been clear to you. So if that's if this is the first time you're seeing that, maybe go ahead and write that down, that y equals sine x squared is the same as y equals sine squared x, okay? We're definitely going to be using that a lot. All right. Any questions about how we would approach example 3? Okay. Got one more thinking question for you here. Okay, so take a moment, think about what rules we know and how we could find this derivative. Okay, so we've got one idea for power rule. So are you saying it would be something like y prime equals cosine x e to the cosine x minus 1? Okay. Okay, so what are our thoughts about this? Anyone agree, disagree? And if we're not sure, maybe let's think back to power rule. Like, when do we use power rule? Not just how do we use it, but when do we use it? Okay, so yeah, exactly. Thank you, Moon. So Moon said the variable is in the base and the number's in the exponent. Now, in this case, though, e is our exponent. Yeah, or e is our base, rather. E is a number. Yeah, but here's the thing. I am so glad you said that, because now I hope that, like, having this sort of public moment of this is a really common mistake, I hope maybe that'll carry over to, like, let's not make that mistake, right? So we have to be really thoughtful. It's not just anytime we see a power. I know, and thank you for always putting yourself out there, by the way. I hope you don't feel like you're picked on. I actually really appreciate your contributions, okay? But when we're looking at this, we don't want to just say, hey, there's a power, let me use the power rule. We got to also think about what's in that base, okay? And so the way that Moon said it is exactly right. We want to make sure that the variable is the base and the numbers in the exponent, then we can use the power rule. But in this case, I think Natalia is saying that we could use the rule from 3.9 and just say that the derivative of e to the x is e to the x, so e to the cosine x should just stay the same. Okay. Now, I will say that in this case, both of these are actually incorrect, okay? I would say this one right here is incorrect because we don't have the right structure for power rule. But this one is also incorrect. And this is probably the way that folks will make that mistake if we watch the 3.9 video. And so one thing that we'll see by the end of today is that the correct answer would actually be y prime equals e to the cosine x times negative sine x. Okay, so this right here is actually going to be the correct answer. And that's something that if we're like, I'm not really sure why that is, by the end of today, we really want to have a solid answer for that, okay? All right, I'm going to clear these pictures. Ah. Okay, this is what you had, right? The building the function composition. Okay, I don't know what happened, but sometimes we just gotta laugh it off. Okay, so this first slide was meant to be the example. And I think for some folks, this slide wasn't really clear. So I just wanna make a few things clear. We are picking different functions, and then whatever we choose on the bottom left, it's gonna pop out what it is when we put G into F. But on the bottom right, it's going to pop out what happens when we put F into G, okay? So pick a function from f of x. Someone type your favorite function into the f of x, and I will go ahead and click that on the screen. So which one of these functions is our favorite one for f of x? X to the 7th. All right. Sorry, Natalia, you've been outvoted. All right, x to the 7th. Okay, what would we like for our g of x? All right, so we're going to choose something from this second column, sine x. Ooh, the last one. Okay, well, let's try sine x, right? So let's say we pick these two, but it'll be such an easy one. If we want to just try what happens if we choose the last one, we can do that right after this. So let's see what happens. If I have f of g of x, then I take sine x, which is my g of x, and I put that into wherever we see the x in the f function, okay? So when I put g inside of f, we get sine x to the 7th, okay? When we flip the order in which we do that, we put f inside of g, we get sine of x to the 7th. And one thing to be careful about here is this means that I'm going to take x to the 7th and I'm going to take that x, raise it to the 7th power first. And then after I raise it to the 7th power, then I'm going to sign it. Okay. What is this one saying on the left-hand side? Does it also say that I'm, okay, yes, this one says that I have to sign the x first, and then we're going to raise that whole thing to the 7th power, okay? Cool. Let's clear that. And let's see what happens if we chose the last one instead. Okay. So now we're mixing x to the 7th with x over x plus 1. And so let's take a look at what's similar and what's different. I'll give you a couple minutes to think about it. And then if someone could explain this one on the left, like what do we do first? And then what do we do second? Okay. Okay, so the first one, we take x and we divide it by x plus 1. Okay, I like that. I like that. So the first thing we do is we do this. Then after we do that, then we raise it to the 7th power. Okay. So we do the fraction part first, and then we raise it to the 7th power. Can someone explain how the right-hand one is different? The g of f of x, how is that different? Good. Exactly. Isaac and Thea, great ways of saying that. We are, in fact, raising things to the 7th power first, and then we put everything into the function. Okay, cool. All right, so you can play around with this as much as you want to kind of build the different functions, but what's more important is as you're building them, think about what's happening, like what's the order and how is that similar or different between the two functions, okay? All right, so now, this is where I've already gotten feedback from folks. It would have been really helpful to have a filled-in example, but let's kind of work through this together so that way we can understand like what the right answer is and why that's the correct answer, okay? So in this case, if I walked up to you on the street and I said, hey, I have this function, y equals 3x plus 5 squared, and I'm going to give you a number for x. And I want you to find the y value that goes with it. Well, what are you going to do with that x first? Are you going to square it first? Are you going to add 5 first? What are you going to do first? Yeah, we're going to evaluate that 3x plus 5 part, okay? So the 3x plus 5, that's the first thing we do. That's considered our inside function. So if you type in 3x plus 5 and you're like, yes, I know that that's the inside function, and then you click submit and it said, please try again, you were probably super bummed out, right? You're like, I'm pretty sure this is the right answer. So this is one clarifying thing. It's asking for the inside function. So in order to make sure we have a function, we need to write y equals here, okay? And once we submit that, then we've got it correct, okay? So if that was a place where you were confused, yes. So this is sort of a not so subtle point that like, no, we got to be like really thorough about our notation. Otherwise, who knows what we're talking about, okay? Okay, so now after you do 3x plus 5, right? What do you do second? We square it, okay? So if you typed in x squared here and you tried to submit that, same thing, please try again because we need to have our y equals there, okay? Then we've got our function. So your answers for the first slide, or this one, whichever number this was for you, should have been y equals 3x plus 5 and y equals x squared. Does that make more sense than maybe when we were doing it earlier? All right, let's try one more here. So what is our inside function here? Or rather, what do we do first? If someone walks up to you on the street and says, hey, I've got this function, what's the y value? Yeah, okay. So learning our lesson from the previous page, we're going to write y equals and then square root. When I type in SQRT, it turns into a square root symbol. So square root of x. You want to make sure you go outside of that square root and then do the +2. Okay. So good work. We've got our inside function. What is the outside function for this particular part? Like after we square root it and add 2, what do we do next? Perfect. Great job, Umar. Y equals x squared. Submit. Good work. Okay. And so there's a couple more for you to sort of look at, but maybe let's do this last one right here. What is, when we say inside function, we also mean what do we do first, okay? So you've been crushing all the questions I'm asking you in the middle of the street, and now I'm like, bam, y equals e to the cosine x. I'm gonna give you a number for x, and I want you to find the number for y. What do you do first? Yeah, y equals cosine, cosine x. All right, good work. All right, so after you cosine the x, what do you do afterwards? Perfect. Y equals e to the x, because that's what we do second. Okay, perfect. All right. So I hope that makes the activity a little bit more clear. If you realize now that you understand how to do it, you can certainly go back and take a look at this on your own time. I think it could be a good study skill just to practice that problem solving piece as well. Okay, but let's kind of exit out of here for right now. My apologies for having, I don't know why there are different versions. I didn't think that could happen in the Desmos, but apparently it did. So, okay. With that, let's hop into the notes for today. Okay, so I think we've got the screen sharing working again. So let's give it a go. Oh wait, hold on. Okay. Can you folks see this? Yes? Yay! Okay. Excellent. All right. So 3.6 is something called the chain rule. And this is one of the most important rules that we learn about derivatives, okay? There's a weird gray block where the meeting controls are in the up in the right-hand corner. Is there still a weird gray block?
Is the top right corner like camera, or because I feel like it's trying to block the stuff that you're clicking on. But it's not there anymore.
Oh, it's not. We good?
Yes.
Yeah, it's fixed.
Is it there now?
Nope.
Okay. Okay. I know I heard it was doing something weird on the videos where it's like covering up part of the screen. I'm really sorry about that. I don't know why these things are happening. Let me just make sure. Okay, I've got optimized for video clip. That should be fine. Hopefully that will avoid the issues of parts of the screen being blocked. Do not panic. It's fine. It's fine. Okay. there we go. Okay. I think something updated somewhere, and I think Notability, there's a bug in Notability somewhere that I have to find, but okay. So anyway, back to the chain rule. This is, as I said, one of the most important rules. Okay, we use it so frequently, but it's one of those rules that if you forget about, then your answer is definitely not going to be correct, but it's going to be like almost correct. And that's like the saddest kind of not correct. Okay, so what do we know? We know that we have our average versus instantaneous rate of change. Okay. We've drawn that picture several times already. We've talked about the differences and the similarities. We've looked at the formal definition of a derivative. That's that really long formula with the limit as h approaches 0. And that's one way to find the instantaneous rate of change. But another way to find the instantaneous rate of change, especially for more complicated functions, is all of these rules that we learned. The power rule, the sum and difference rule, the product rule, the quotient rule, the derivatives of trig functions, also the derivatives of exponential and log functions, okay? And so at this point, our brains should be feeling rather full with all the different rules, okay? If you are a person who makes reference sheets for an exam or sort of like a one-page study guide for yourself, I would really encourage you to start listing out all those rules and making sure you know what those are, organizing them in your brain so that you're ready for to use them at any given moment, okay? Now, what's new? How do we find the derivatives of nested functions? And so what I mean by nested is this last example we looked at on Desmos, y equals e to the cosine x. That's a really great example of a nested function. You could also think about this as function compositions. Okay, so anytime we see a function composition, chain rule is going to be our best friend. Okay. So intro, make sure you've looked at that activity. We went over it a little bit, but please go back and kind of think about it a little bit more if you feel like you need to really make that concept sticky in your brain. Okay, but today's class is really around doing a bazillion examples. All right. And so some of these examples should look familiar because they were in the slides for the Desmos activity, right? Now, one of the things that we saw in the very last slide on Desmos is that you got the chain rule, you got the actual rule for that, okay? Anybody happen to have that written down? What is this chain rule? Perfect. Okay. So the chain rule is, let's say that you have given f of g of x. Okay. So you're given a situation where you have an inside function and an outside function, or rather a function that you would do first and then a function you would do second. So given that, the derivative is exactly like Graham said. We take the derivative of the outside, so f prime, and we do not change the inside piece. So we sort of imagine for a moment that only the derivative of the outside is happening. And then we work our way in. We multiply by the derivative of the inside piece. Okay. Now I know that the notation can look kind of scary or intimidating, so I thought we would just jump into some examples and try this rule out. Okay. All right, so example 1. What do we have as our f function, our outside function? Okay, we have that x squared, right? This one is the outside function. Okay. And what do we have for our inside function? (3x minus 5). Okay, so this is our inside function. Okay. And if I use the letters that we used above, we might call this outside one f of x. And this inside one we would call g of x. Okay. And so if we want to find y prime, or our dy dx, or our derivative, the rule says that we're going to take the derivative of the outside function, so the squared. Okay, so if I had x squared, what's the derivative of x squared? 2x. Okay, now instead of saying x squared, I'm saying we have something squared. What is the derivative of something squared? 2 times something. Exactly. Okay, so the derivative of f is going to be 2 times our something. Okay. So what we have so far, this is the same as this part. Now we're going to multiply by the derivative of g of x. We have g of x is 3x minus 5. Excellent job, Aylin. That derivative is going to be 3. And that, again, comes from our g prime of x. Okay. Let's clean this up a little bit. I might take the 2 and the 3 and multiply them, so I get 6 times 3x minus 5. This would be absolutely fine. Since this power is a 1 here, I could distribute if I wanted to, and I'd get 18x minus 30. Okay.
Professor, I have a quick question.
Absolutely. What's up?
So do you want us to leave it at that final 18x minus 30, or do you want us to leave it in the unsimplified form?
Oh, okay. I would say for this one, either one is okay. The only reason we can simplify is because that power is 1. So for example, if I had up here instead a power of like 3, you can't distribute and then cube it.
Oh, okay. Thank you.
Okay. Okay, let's see. We got some questions in the chat. Yeah, it's kind of like the product rule in a sense. Okay, yeah. All right, and second question, do we mark the outside function as f of x? I think a lot of textbooks do call the outside function as f of x. You can also just call it the outside function if you want. So that's sort of a personal preference, okay? All right, next question. I'm not sure if I missed it, but how do you know f of x is inside and g of x is, or f of x is outside and g of x is inside? That's a great question. Is there anyone who feels like they might be able to summarize that? Like, how did we know that we have this outside and inside function?
I wrote it down as the inside is the first thing you do to x, and the outside is the second thing you do to x. I don't know if that's helpful.
Yeah. How does that sound as an explanation? Folks who've had that same question. I think that's a pretty good one. So inside is what happens first to the x, like if you plug in a value for x, and then the outside is like that other function. So what happens second or what happens next? Okay. Yeah, this ties back to those questions we saw in Desmos. Somebody walks up to you on the street. What do you do first? What do you do second? Okay, so what you do first, that's your inside one. What you do second, that's your outside one. Okay. All right. So let's try identifying here. What do we have for an inside function for example 2? Or rather, someone walks to you up on the street, says, here's this function. What are you going to plug in first for x? Yeah, exactly. So we've got this as our inside function. And typically we call that g of x, but you could call it whatever you want. Okay. And our outside function here. After we do that square root of x plus 2, then we square it exactly. All right, so we've got our inside function, we've got our outside function. We'll go ahead and plug those into our chain rule formula. And so we'll get y prime equals, let's see, what should I write down for the derivative of the outside function? This will be the derivative of our outside function. What should we write there? Awesome. Okay, derivative of x squared is 2x. We know the derivative of something squared is 2 times that something. So 2 times that something. Very nice. Okay, now we're going to multiply by the derivative of the inside piece. So g prime of x, I only want the derivative of g. I'll give you a moment to maybe compute that. All right, what do we think? X to the negative 1/2 is close. I agree, we need that coefficient of 1/2 there. Okay, so we're gonna get 1/2 x to the minus 1/2. And what happens to the 2, the plus 2 at the end of the g of x? Lovely. Okay, good. Now, in case this is where your 1/2 went to, if we're sort of combining things and we're simplifying, we could take this 2 and this 1/2 and multiply them, and we would get 1, and then we wouldn't have the coefficient there anymore. That's okay, okay? So if we were to clean this up a little bit, we could get 2 times 1/2 x to the negative 1/2, and then times the square root of x plus 2. And if we clean that up a little bit more, we get square root of x plus 2 over square root of x. Okay. So a little bit of algebra and some reducing and rewriting of things. That's what we get. Okay, let's see. Is this a good way to summarize or explain the rule? We are taking the derivative of f of g of x like it was f of x. But then we multiply it by g prime because we have a g of x instead of f of x, or instead of x. Yes, I think that is a wonderful way to summarize that. Okay, so folks, maybe copy that down or take a screenshot of that chat. I think that's a really good way of summarizing what we're doing here. Okay, it's almost like we're subbing out that g of x for a split second, but then we have to compensate for the fact that g of x is not just an x. Okay. All right, let's take a look at, let's see, what time is it? Let's take a look at one more example here. Maybe we'll take a break on the earlier side and then come back and really dive deep into some of these examples. All right. So example 3 here, we've got y equals sine squared x. What is our inside function? Like, what do we do first? And what is our outside function? Or what do we do second? Okay. So I think the trick to answering this question maybe lies in writing this in a way that we would never write it, but really thinking about what it means, okay? So sine squared x is the same as sine x. So you sine something and then you square it. Okay, let me say that one more time. Sine squared x is equivalent to sine x, and then we square it. Okay, now what's your outside? What's your inside function? Outside is x squared. Good. So this is our outside, or our f of x. Perfect. And the inside is our sine x. Does that make sense? I know someone had said that they're both sine x, but that would be like if we're looking at product rule. If we're using product rule, they would both be sine x. But if we're looking to use chain rule, then we're really thinking about like, what do we do first? What do we do second? Okay. And I think we already had an answer in the chat, but let's unpack that. So y prime.
Professor, I just had a quick question then.
Yes. What's up?
So would we get the same answer if we use those different rules? Because you could use product rule, correct?
Absolutely, you could. Mhm.
And we would get the same answer if we use chain rule?
Yes.
Okay, all right,
Yes.
thank you.
Good question. Mhm. All right, so y prime, if we follow the same idea we've been doing before, and we set this up to be the derivative of the outside piece, pretending like the inside were an x, we would get 2 times sine x. And then if we multiply by the derivative of that inside piece, what is the derivative of sine x? cosine x. Very nice. So we multiply by cosine x and we'll get 2 sine x cosine x as our derivative. Okay. Moon asked a great question before we go on break. Let me just show you real quick how you could do this using product rule. So sine x times sine x would mean we're using product rule. Your u would be sine x. Your v would be sine x. du is cosine x. dv is also cosine x. You plug those into your product rule, you get u dv plus v du. You have 2 of them, so 2 sine x cosine x. Same answer. Okay, yeah, really great question. Okay. All right, so I think on that note, let's take a break. It is 10:29. Let's be back at 10:40. All right, let's be back at 10:40 a.m. and then we'll work through the rest of those examples and get even a little bit more complicated and see how things go. Okay. All right. So here we are back with the chain rule. We revisited 3 of the 4 problems that we saw in the Desmos activity. Now we're taking a look at the 4th one that we saw, okay? So the one where we had y equals cosine, or y equals e to the cosine x. And there were a few guesses about what that derivative was, right? But now that we know we're looking at something sort of in that structure of outside versus inside, or what do we do first and what do we do second, how might we label example number 4 to have an inside function and an outside function? What might that look like? Okay, which one is which? So we've got e to the x and cosine x. Which one should I label as my inside and which one should I label as my outside? Okay, so we've got inside for e of x. Oh, outside. Okay, so that means that this sort of e is our outside function because that's what we do second. Right? We said earlier, someone walks up to you on the street, they hand you this function. You're going to cosine that x first, which means this is your inside function. Okay. Perfect. Exactly. G of x equals cosine x. All right. So let's find that derivative. We're going to need to find the derivative of the outside. So our f prime of g of x. And then we're going to have to multiply that by our derivative of just our g prime of x. All right, so derivative of the outside function. What do we get when we take the derivative of e to a power? The derivative of e to something gives us the same thing, okay? So we'll get e to the cosine x, all right? Now, this is where that other part came in, right? Because earlier we were looking at Desmos and I was like, it's not really the right answer either. Now we have to compensate for cosine not being just a regular x. And derivative of cosine is negative sine x. Okay. So when we write these out, typically we move like the trig function to the front. So we'll have negative sine x and then e to the cosine x. And that is the derivative for e to the cosine x. Okay. Any questions about number 4? All right. Well, let's take a look at example 5. Okay. So same thing. I'll give you a moment to think about this. What do you think is the inside function, or what is your g of x, and what is your outside function, or your f of x? Okay, so we've got one that says x squared is on the inside. One says x squared plus 1 is on the inside. All right. I think it would probably be beneficial to grab the whole piece as the inside function. Okay, so x squared plus 1. The reason why is because we're taking that whole thing and then we are square rooting that whole thing. Okay. Yeah, square root is on the outside. Now, it might even be helpful to write the question like this: x squared plus 1 to the power of 1/2. That might be a little bit more obvious to us that the outside function is the 1/2 power and the inside function is the x squared plus 1. Okay. So that was one benefit of like learning how to rewrite all these things, is sometimes it's just easier to see what's what. Okay. Yeah. Okay, cool. All right, so now if we have y equals x squared plus 1 to the 1/2, I think we can see our inside function is x squared plus 1, our outside function is the power of 1/2. So when I take my derivative, I can find the f prime of g of x. So I'm going to pretend that I just have something to the 1/2 power. And then I'm going to take the derivative of the inside piece. And I'm going to multiply those together. Okay. So derivative of the outside is going to give me 1/2 x squared plus 1 to the negative 1/2. Okay, so all I did was use the power rule there. And then my derivative for g prime of x is just going to be 2x plus 0. Okay. You don't have to write the 0. It's just there for some of us who maybe want a little reminder. What happened to the 1? Derivative of 1 was 0. Okay. And if we clean this up a little bit, we'll get 2x over 2 square root of x squared plus 1. And those 2's in the front can reduce. And so we'll get x over the square root of x squared plus 1. Okay. So let me sort of get these both on one screen here. How are we feeling about these two examples? Like identifying inside versus outside, or what comes first and what comes second. All right, we got a 4 out of 5 and not too bad. And a whole lot of silence. I don't know what that silence means. So, okay. Okay, shall we practice some more? Try out some more things? Yes, okay. Woo. All right, so let's try using a table. Okay, so we know what the rule is, and now these questions are like the ones where we strip away the function, like we don't actually know what the function is, but we really have to drill down and understand the concept of what we're doing. Okay, so let me just show us how to read the table real quick, and then we'll take a look at the examples. All right, so tables like this can be really overwhelming sometimes because there's so many different columns, but if I asked you to find f of 2, can someone annotate on, I don't know if you can annotate right now. Can someone annotate on the screen which box shows me f of 2? Yes, that's our f of 2, right? How did we find that? Well, we knew we wanted f and we wanted 2. And so we go f and 2 and we get 1. Does that make sense? Okay, let's try another one. What is f prime of 1? Yeah, f prime of 1 is 4. Okay, I don't know what the function is, but I know at the point 1, the slope is 4. Okay. What about g of 3? Feels like a bingo game now, right? Find g of 3. Put a little piece of paper on your bingo square. There we go. Okay. And let's go one more. Let's go g prime of 2. G prime of 2. Yeah, g prime of 2. Okay, so does that make sense how we read the table here? I think that's honestly one of the hardest parts, is reading the table. Okay, got one yes. I hope there are more yeses, that people are just not feeling like they want to type. Okay, all right, so now let's take a look at question 6. So question 6 says that I have h of x equals f of g of x. And we want to find the derivative of h at the point 1. Okay. So the first thing we should do is find the general derivative. Okay, so don't plug in numbers yet. Your last step will be going to the table and finding the numbers and plugging them in. Okay, so don't plug in numbers yet. But if I have h of x equals f, and then g is inside of f, what is h prime of x? Okay, so let's look for that first. What is h prime of x in terms of f and g? In other words, what is our outside derivative? Yeah, and our inside, exactly. We've got f prime of g of x times, hold space for that, g prime of x. Okay. Now I think this step is really hard because it's so concept based and you don't have any numbers to work with, right? You're just saying like, what is the formula that we're using here? Okay. The second step is where we get to actually put in the numbers and find a number answer. Okay. So now we're going to sub in x equals 1. Okay. So h prime of 1 equals f prime of g of 1 times g prime of 1. And so just to highlight that a little bit better, then I plugged in 1 here, I plugged in 1 here, and I plugged in 1 here. Okay. Can someone tell me what g of 1 is? G of 1 is 2. Good. So I'm going to write f prime of 2. Okay. So instead of f prime of g of 1, I put f prime of 2. Can someone explain how I was able to do that?
Because g of 1 is inside the f prime.
Yeah, g of 1 is a number that we can actually find from the table. So all we did was, let me see how we're going to make this work. All I did was take g of 2 or g of 1 and replace it with 2 because that was the number from the table. Exactly. Yeah, that's a great way of saying that. We know g of 1 is equal to 2 and it's inside the parentheses. So now we can go to the table and find the number. Okay. What can I write for g prime of 1? Good, very nice. 6. Mhm. Yeah, exactly. Yeah, we can think about them as y values. All right, now we're almost done though. We haven't quite gotten our numerical answer. The last value we need to find is our f prime of 2. Okay, so for f prime of 2, we're going to plug in 5. Good. So I've got 5 times 6, which equals 30. Okay. So let me leave that on the screen for a moment. Have you finish copying that down? Let it marinate a little bit. Let's see if there are any questions before we kind of move on to some of the other table questions. We feel okay to try example 7? Yes. Got one yes. Yep. Okay. All right. So let's take a look at number 7. So this time we don't have an h of x, we have a k of x, and k of x is defined to be g of f of x. What's different? What did we change in example 7 from example 6?
G is now outside and f is inside of g.
Yes, that is so correct, right? In example 6, f was the outside function, but in example 7, g is the outside function. Okay, and so I think it was Aylin had a question earlier about like, is f of x typically the outside function? It is, but sometimes they switch the letters on you. So you really have to think about like what's on the outside or what do you do first versus second. Okay. So with that, let's find our general derivative I'm going to write k prime of x equals, and what should I write here? Okay. What should I write for my general derivative? All right, g prime of f of x, good. G prime of f of x, because that's the derivative of the outside. Mhm. And then f prime of x, because that's the derivative of the inside piece, all right? Does that make sense to folks how we were able to change the formula based off of the new letters that we had in this example? Yeah, okay. All right, let's sub in x equals 1. We're going to get k prime of 1 equals g prime of f of 1 times f prime of 1. Okay. Now I can turn this into g prime of a number. What is that number? G prime of 1, let's see. G prime, oh no, f of 1 is 3. Very nice job. Okay. And then for f prime of 1, I can go ahead and put a 4. Right? So f prime of 1 on the table is 4. And then last but not least, I got to find g prime of 3. And what number does that give us? 9, perfect. So 9 times 4 equals 36. Okay. All right. So at 1 second, this particle is moving at 36 units of velocity. Yes, exactly, exactly. If k of x were a position function, you could certainly say that the velocity at t equals 1 is 36. That's a great way to think about it. What is a real life application of specifically chain rule? So I think it would be really nice if every single function we could model was like just one function, like just an x squared or just an e to the x. But I think the reality is when we're modeling, we actually have to consider a bunch of different functions, function types. And so when we start to mix and match function types, then we're really looking at like needing the chain rule to help you find a specific thing. Okay. So for example, in one of the classes that I'm taking right now, we are, can you guys see that?
Yes.
Yeah, okay. So in one of the classes that I'm taking right now, we're looking at things that model heat inside of a given shape. And so, for example, in this particular question, we were looking at something called Laplace Equation, which looks at the heat transfer in a specific situation. And so in this particular case, in question number 3, we're looking at it inside the shape of a triangle. And so you'll notice like some of this notation might seem a little familiar. Whoops. Where we have like, do you see how it says du dx, but it's like a curly u? So one of the things that you sort of learn in, this comes up in, I think, Calc 3, is sometimes we don't just take derivatives with one thing changing, but there's more than one thing in the equation that's changing. So for us, we only do single variable, meaning like X is the only thing that's changing. But in Calc 3, you take a look at things where X and Y are changing. Okay, so if we think about a rectangle, it could change its width, it could change its length, and wherever you are in the rectangle, you have to know where you are and what the change of the heat is at that particular place to help you solve a problem. And so I think I actually did use chain rule somewhere here. Hold on. So in order to find this particular derivative, at some point you have to use chain rule, because this cosine of n pi x over L, we have to accommodate for that. We get that n pi over L. That's our derivative with respect to x. So it's actually really useful in a lot of like more complex modeling situations, okay? Anyway, you don't actually need to know any of that I just showed you, so don't freak out about it. But it is very useful when we're modeling different types of functions. Yeah, so there's like the heat equation, there's a wave equation to model like sort of like vibrations of strings if you're thinking about a stringed instrument. Or if you're looking at the top of a drum, like that membrane and how the membrane vibrates over time. So you're going to need like a lot of different things to model that kind of stuff. Yeah. So yes, even in those other classes, you'll use chain rule. They're not usually super complicated cases. You just have to remember to do it. Okay. All right. I did include 2 questions here that were just a review of product rule and quotient rule. I will do these before I post the notes, but I feel like I wanted to just include them in here so that we get used to using the table in a variety of ways, okay? So it's like a table doesn't mean it's always going to be chain rule. It could be product rule, it could be quotient rule. So, you know, I'll leave you to do example 8 and 9 on your own time, and you can check those with the notes once they're posted, okay? It seems like overall, though, we're doing better with using the table to read the values. So that part I'm actually really happy about. I feel like the first time I showed you a table, everyone was like, what is happening? So this is good. I think there's a little bit more comfort around that piece. Okay, so let's move on. Got a few more examples here. So let's go back to this idea of rules. And now with this next chunk of practice problems, we're looking at rules that might include more than one rule, okay? So that's really the tricky thing, right? It's not always just power rule. It's not always just product rule. Sometimes you have to mix and match and use that to help you figure out the derivative, okay? All right, so let's take a look at example 10 here. We've got y equals x to the 5th minus 4x plus 8, all raised to the 7th power. And so before we start taking a derivative, my question to you is, what rule or rules do you think we will need to find this derivative? Don't everybody speak at once. Okay. All right. We got a chain and we got a power. All right. So we know that we have, let's stick to our colors here. We've got sort of it's not how you spell outside. We've got an outside function that we can call our f of x. And we've got this inside function that we can call g of x. And I really like how thorough we were in saying what rules do we need. So to take care of the fact that we have an outside and inside function, we're going to need to use chain rule, okay? And to find the derivative of just the g of x, we'll need to use power rule, and we use that also for the chain rule, okay? So y prime equals, what are we going to get for that first derivative, or the first part of it, and what are we going to get for the second part? Give you a moment to think about that and write that out into the chat. All right, so power rule says we bring that power down, we keep the thing in the inside, and we lose a power. So 7 minus 1 gives us 6. Very nice. All right, so that is, as Yitan said earlier, we're thinking about it like the whole thing in the parentheses is just an x. And so we do 7 times that something, lose a power, 7 minus 1 gives us 6, okay? Now let's consider the derivative of g of x. All right, what do we get? 5x to the 4th minus 4 plus a 0 if you'd like. Very nice. Now, as far as simplifying, there's really not a lot that I would say that you need to do. Maybe, if anything, you bring the 7 and this piece together to the front, and then you finish with the thing raised to the 6th power, okay? So what I mean by that is it might look something like 7 times 5x to the 4th minus 4 times x to the 5th minus 4x plus 8 to the 6th. All right. There's no expectation to FOIL that out. 100% do not do that, okay? I don't need to see it. You don't need to do it. You can just leave it as something to the 6th power, okay? If you wanted to, you could make this into 35x to the 4th minus 28, but you don't have to. It's also perfectly fine to leave it like this. Okay. How do we feel about number 10? Would we get marked down for just, meaning like if you didn't have, if you didn't have this part? Oh no, you don't need to write that. You do not need to write that. I think one of the things that actually is a little harder right now is like, I don't always know if people need to see that 0. So I'm going to continue writing it for a little bit longer, just so that when people go back and study, they're like, oh yeah, the derivative of 8 is 0. Okay, but you don't have to write that. Okay. All right. Well, let's take a stab at number 11. Okay. First things first, before we start calculating, I want us to think about what rules we're going to use in order to find the derivative. And specifically, if there's more than one rule, I want us to think about what order we need to use those rules in, okay? All right, I got a product and a chain. Which one do folks think comes first, product rule or chain rule? Oh, and power rule. So of those, which one comes first? Tell me why you say that chain rule comes first. Because we did it first last time. Because both of them have an inside and an outside. Good. And we have to find the derivative of each factor. Okay, cool. All right. So I guess in my head, I was sort of arranging it differently, but I understand what you folks are saying. So in my head, I had thought here, we're gonna need the product rule. So that's sort of like my bigger rule. And then in order to find like du and dv, then I need to use chain rule. But I think we're saying the same thing. Okay, I think we're saying the same thing. So if we set up for our product rule, we'll get u equals 3x plus 1 to the 6th. Oh, make it one big thing. How? Like this, you mean? Okay, but how does that help us find the derivative? Okay. So let's think about what we're looking for, right? We're looking to find dy dx, which means we got to figure out how to find the derivative. And so at some point, our answer might start to look something like this, but we want to think about sort of what steps we need to take to get there. Okay, kind of like an order of operations thing. And so because we see some sort of product here, like we're multiplying, what we want to start our setup with is the product rule. Okay, it's almost like if we go back to that, I walk up to you on the street, I give you a function, I'm like, plug in some numbers for X, how do you find Y? I bet we would say something like, I would find this first, right? And then separately, I would find this, and then I would multiply them together. So now to solve that, we're going to sort of unpack that in the opposite direction. Like we're going to go for the product first and then find the derivatives of each part and plug those into the product rule. Okay. And it's okay if it doesn't make sense quite yet, I think that we've got, yeah, exactly. We've got a lot of different letters going on here. Yeah, yes, exactly. That is where we're going with it. Yes. Okay. What do we get for our du here? So if u equals 3x plus 1 to the 6th, what do we get for our du? Okay, so 6 times 3x plus 1 to the 5th. I would say that that is almost right. What do we need to consider? Nope, we don't want to FOIL this. We didn't use the chain rule yet, right? We found our derivative of the outside piece, but we didn't find the derivative of the inside piece yet. Okay, so remember outside, or what we do second, and inside. Okay, so we're just looking at that 3x plus 1 to the 6th. We haven't even looked at the root part yet. Okay, but when we're taking our derivative for u, that's where we need chain rule. Okay, so the derivative of 3x plus 1 is just 3. Oops. And so I could write this as 18, 3x plus 1 to the 5th. Let me pause for a moment, let you write that down. Make sure we understand where that 3 came from.
Professor, I have a question.
Absolutely, what's up?
I'm a little bit confused about how the chain rule plays into the du part. So do we find the derivative, the du using the using the power rule and the chain rule? Or am I like completely missing this?
So if I just gave you this, I said y equals 3x plus 1 to the 6th. And I said find y prime. We would use chain rule. We'd take the power down, we bring it, we'd lose the power, right? And then we would multiply by the derivative of the inside function.
I see what I was missing. I'm sorry. My screen is super blurry for some reason, and I think I just like missed half of what was on the screen. I'm really sorry.
Oh, you're fine, you're fine. This is a hard problem. This is one of the first ones we've seen that sort of mixes and matches a lot of rules. Okay, that's why I wanted to leave a lot of time for this. But we're almost imagining this as sort of like 2 different problems for a moment. Like we're finding our u and our du. And to find our du, we need chain rule, right? Does that part make sense to folks? It's okay to say no. Mostly. Okay. Okay. All right. So we have our v here, but knowing that I have to find the derivative of this, there was one way that I rewrote something like this before that made it click a lot more for a lot of people. How did I rewrite this so that we could really clearly see what functions we're dealing with? When we have this part right here, square root of 2x minus 5. Yeah, well, as soon as I wrote this as 2x minus 5 to the 1/2, so many more people were like, oh, now I see the inside and the outside functions, right? So we've got our outside function of the power of 1/2. We've got the inside function of 2x minus 5, okay? So if we find our derivative, we'll get 1/2. We'll get 1/2 2x minus 5 to the negative 1/2. That's going to be my derivative of the outside function times, I have to consider the derivative of the inside function. So derivative of 2x minus 5 is 2. Okay. So before we simplify anything here, how are we feeling with that? Chain rule just to find dv. Does that make sense? Now that we're sort of viewing it as 2 separate problems? I feel like when there's so much silence, either my microphone is not working or we feeling really stuck. So help me out a little bit here.
So we get the 2 by solving the inside of the function.
By taking the derivative of that inside function.
Okay.
And that's really similar to how we found that 3 for the du. The derivative of 3x plus 1 was 3. Okay. All right, well, let's finish this problem, right? See how it goes. But if we want to find y prime, what the product rule says, I need to use u dv plus v du. Okay, so we're just going to plug in the parts that we have. And I suppose we could have simplified this dv and get 1 over square root of 2x minus 5. Okay. But if we just plug everything into the formula now, we're going to have u times dv plus v times du. Okay. That's just plugging it in. Are we okay with where all the different pieces came from? Now, I saw earlier in the chat, someone was like, I don't want to deal with all the algebra. It's really not a lot of simplifying that I expect you to do here, okay? Maybe at the most, something like this, 3x plus 1 to the 6th over root 2x minus 5. So I'm just combining the first term into a single fraction. And then for the second part, maybe something like this. Just because the constants tend to go in the front. Whoop. But that's it. That's it in terms of simplifying. Okay, there's not a ton to simplify when we're looking at like a lot of the more complicated derivatives. Like if you look back at, if you think back to that homework assignment that I shared with you on the screen earlier, sometimes there's just not a lot to simplify, and that's okay. It's part of this like maturing as a mathematician that we can sit and look at an answer like this and be like, yeah, that's fine. Okay, not everything is going to boil down to a number or just a single function. And it's okay if we don't even know what to do with all these pieces. We can just sort of, part of this is just being comfortable with having all those pieces there. Okay.
Could you explain it? This is more like an algebra question, but could you explain again how you turn this into that? Because I know that the negative pretty much like brings the thing down, and then I'm not really sure.
So let's see. The first term, the pink term, would be 1 over 2, because that's the 1/2, right?
Yes.
And then 2x minus 5 is a square root, but it's on the bottom. Right? Because the power of 1/2 is the square root, but it's a negative power, so it's on the bottom.
I see that.
Okay. And then times 2 is really 2 over 1. And so the 2 and that 2 reduce, and we're only left with 1 over the square root of 2x minus 5.
Okay, that makes sense. Because I figured out the 2 part, but then I didn't know why it was a root. But that makes sense, yes. Okay, thank you.
And yes, that is actually a very true statement here. So chain rule is like a new shiny thing, but it comes up in a ton of different problems, okay? And we really need to focus on what it looks like with other rules. So if you're looking for practice problems outside of class, I would encourage you to try questions sort of like this, where you're needing to use more than one rule to solve a problem, okay? So Christina, we are using product, but in order to use product, we need to use chain rule. So this top part is like the setup for product rule. We didn't actually use it yet. We use it down here. Okay, yeah. So we don't use the product rule twice. It's just that in setting up for the product rule, we'll need some other rules, okay? And that's actually something I would encourage you to do in tutoring or in your own study groups or during office hours, is just sit and think about like what order you're going to use rules in, or just practice identifying the rules that you need. I think that's actually a really good study strategy, okay? All right, let's take a look at example 12 here. So I've got y equals tangent cubed for x. What rules do we think we might need here? Give you a moment to look at that, think about it. What rules might we need? Chain rule, I agree. Chain rule is going to come in handy. What else? Power rule, I see a power of 3. So yes, that's telling me I probably need a power rule. And then just because we see the tangent, we're thinking we also need to know the derivatives of tangent, okay? Okay. So if we're needing chain rule, what is the outside function here? X cubed. Okay. I wonder if we took the time to write this as y equals tangent 4x cubed, that might make it easier to visualize that our outside function is x cubed. I like it. Okay. What's the inside function? Okay. Seeing a lot of folks saying tangent of 4x is the inside function. Okay. So let's go back to our encounter on the street. I walk up to you, I say we've got y equals tangent cubed 4x, and I give you a number for x. What do you do first to it? Multiply by 4. Okay. Multiply by 4. That's the first thing you do. What do you do next? All right, you tangent it, you find the tangent, you tan it. Apply sunscreen though. All right, so times 4 is first. Tangent is second. Then what do? Then you cube it. Okay, so multiply by 4, tangent, cube. Awesome news about chain rule. You can have a bazillion functions inside of other functions. And you can still use the chain rule, but you would have to apply it the appropriate number of times. Okay. So I'm going to erase this green circle for a moment. All right, so we've got our outside function is the cube. Our inner function is the tangent. And we've got one more function that is the innermost function. Okay. So we've got 3 functions here. We can still use chain rule. We're going to work our way from the outside all the way into the inside. Okay. So y prime is going to be, the first thing will be 3 tangent of 4x squared. Okay, so I use the power rule to find the derivative of the cube function. What is the derivative of tangent? No, it is not cosecant. It is secant squared, okay? So make sure you got the list of those 6 derivatives written down, but the derivative of tangent is secant squared. What am I gonna put inside the parentheses? The 4x, okay. So I've got the derivative of the outside. I've got the derivative of sort of like the middle one. I got to do one last thing. I need to find the derivative of the insidemost function. Derivative of 4x is 4. Okay. So before we simplify, we looked at this problem. It actually had 3 different functions nested inside of each other. Since we have 3 functions, we need to multiply 3 different derivatives to get the derivative. Okay. Now, I would not do this to you, but what if you had 10 functions nested inside of each other? How many things would you be multiplying? I hope not, Graham. Only 10, only 10. Okay. All right. So if you had 10 functions that were all composed inside of each other, that's fine. Then you would multiply 10 different derivatives. If you had 100 different functions, you would multiply 100 different derivatives. Okay. Now, if we're combining these, this is really about the simplification that I would expect. I would expect that the 3 and the 4 get multiplied together to be the constant in the front. Okay. Then it doesn't matter which one comes first, but then we'll have our tangent squared for x and our secant squared for x. Okay. This would be our derivative of tangent cubed of 4x. All right. Any questions about what happens when you have more than just an inside and an outside function? Okay. Well, before the brains explode, we have one last example here. Okay, we got one last example. So as you start to prepare for the exam next week, it's really vital that you start to consider how all of the different sections in the textbook work together. So like 3.5 was about trig. 3.6 is about chain rule, but sometimes we use them together, okay? 3.3 was where we learned about horizontal tangents, but we can still use that idea with new types of functions, okay? So let's cap off today with example 13. Determine where the function y equals cosine 2x plus 2 cosine x has horizontal tangents over the interval 0 to 2 pi. Okay. So someone remind me, when we're looking for horizontal tangents, what are we looking for? Like, how do we connect what we learned about calculus to the idea of a horizontal tangent? I love that. Okay, horizontal tangents means where the slope equals 0. How do we write that in terms of, yes, and the diagram, perfect. Now, how do we write that in terms of calculus notation? Like instead of saying slope, we have another way of saying slope. Derivative. Okay, so we're really saying y prime equals 0. Exactly. Okay, so that again is a connection I want to make sure we have real tight in here. Horizontal tangent slope is 0. That's awesome. But now we need to feel comfortable in that next step too, that slope means derivative. And so we're really looking for where the derivative equals 0. Make sense? Not sure. Okay. All right. So what we're going to do then, if we want to think about it in terms of steps, is we're going to find our y prime. Okay, so we're going to find our y prime. After we find our y prime, what's our second step going to be? Someone sort of think ahead. After I find my y prime, what am I going to do? Good, good. We're going to set y prime equal to 0 because we're looking for a horizontal tangent. Excellent, excellent. All right, and then once we do that, we're going to solve for x. All right, so those 3 steps have been consistent ever since we learned about horizontal tangents. Now we're just throwing in new rules about how we find them, okay? So let's find our y prime. Y prime equals, all right. What rule might I need for the cosine of 2x? To find that derivative of just cosine of 2x. All right, so using the derivative of cosine, we get the negative sign. And excellent, great job, Moon. we need to consider that we have sort of an outside function and an inside function. How tricky is that? I'll let you answer that in the comfort of your own home, okay? But chain rule comes up so much. So I think we've got a good first part of that derivative, negative sine of 2x, but then we have to multiply that by the derivative of 2x, which is 2. All right, so we've got our derivative of the outside and our derivative of the inside. Exactly. Yep, and we certainly need trig as well. Yes, thank you, Graham. Okay. So y prime, just that derivative of the first term, we get something like this. Plus, how do we find the derivative of 2 cosine x? Do we need chain rule? What do we need? We could use product, all right? But I want us to really leave the idea of product rule at home for a question kind of like this part, okay? In particular, 2 is a constant. So we can just use the constant multiple rule. That will save you some time. While product rule will work, it will save you time to use the constant multiple rule, okay? Meaning that we'll have 2, which is the constant, times the derivative of whatever function we're looking at. Okay. So since we're going to be doing something with this, let's clean this up a little bit, see what we get. Negative 2 sine 2x minus 2 sine x. That's what we get for our derivative, okay? Now we got to set this equal to 0. So we get 0 equals negative 2 sine 2x minus 2 sine x. Okay. Now, if I want to solve for x, which I do in this case, it might be a good idea to see what I can simplify and rewrite, okay? So I'm going to divide both sides by negative 2. And then I'm going to use a trig identity to make a substitution. Anybody happen to remember what the sine 2x equation is? One of the identities that you learned in trig. Yeah, 2 sine x cosine x, good. So we get 0 equals 2 sine x cosine x plus sine x. Great. I'm going to factor. That will give me 0 equals sine x times 2 cosine x plus 1. Okay. From factoring, because they're equal to 0, now I can write 2 separate equations. sine x equals 0 and 2 cosine x plus 1 equals 0. We call this the zero product property. And I'm writing that out because the zero product property, you got to have it equal to 0 in order to use it. Okay. All right. Well, let's see how much trig we remember. Got to find our unit circle values. We should get x equals to 0 and pi on this side. And this becomes cosine x equals -1/2, or x equals 2 pi over 3. Yeah, 2 pi over 3 and 4 pi over 3. And so all together, we'll have 4 answers: 0, 2 pi over 3, pi, and 4 pi over 3. Those of you who were with me in trig, this is the moment where I was like, we really need to know how to solve these equations because at some point it's going to be part of a bigger problem. Here it is, as promised, part of a bigger problem, okay? What if you forget how to? Yeah, so trig definitely doesn't go away. That's why there's that trig review activity on Desmos. I know that it's easy to forget like what's important and what's not. So go use that at your own time to kind of brush up on things. But yeah, exactly. You still have all of the old recordings and stuff too. That was actually another reason that I asked you to make reference sheets in the fall, like it was mandatory, because I wanted you to have a 1-pager that you could go back to and be like, oh, all my formulas are here. Okay, I know that was a lot of delayed gratification because here we are months later, but if you have your reference sheets, a lot of this stuff should be on your reference sheets. Okay. All right. So,
Professor, sorry to interrupt. I just had one question about the steps.
Yeah.
For number 2, when you divided out the -2,
Mhm.
are you dividing both sides like 0 by -2 and the
that is exactly correct.
okay, all right, thank you.
You're welcome. All right, so here we are. We will see this kind of stuff a lot. Again, this is sort of what makes calculus hard. I wish I could say that it wasn't, but what makes it challenging is you got to know your algebra, you got to know your trig, and you got to know it all in the context of other stuff. Okay. So with that, I'm going to go ahead and stop the recording.